Welcome everyone, the PX4 community members and all the others who have joined us today on this amazing event. And welcome everyone who come to see our discussion concerning atmospheric monitoring by drones. Let me first introduce myself and the people who will be joining us for discussion. I'm Petra, and I'll be serving as a moderator in the discussion. And I'm a co-founder and president of ThunderFly, which is a Czech-based company specializing in development and production of unmanned UAVs that are designed to operate in unfavorable weather conditions. Then we'll have Roman, who is also a member of ThunderFly core team. He's a software engineer currently working mainly on software for visualization of measured data and its processing. And then we have Jakub, who is airspace engineer working for Czech Technical University, who is currently engaged in a project centered on detection and dosimetry of ionizing radiation. So welcome everyone, and let's see what we'll be speaking about during this session. So at first, I'll very briefly summarize the current state of atmospheric monitoring measurements for those of you who haven't heard of them yet. And from this, we'll see what challenges are we facing in this field. Then I'll ask Roman to somehow share an idea of an optimal structure of how such system for atmospheric measurements should look like. And then we'll focus on examples of solutions that we've designed during the previous years. And of course, and at the end, we want to stress what are the benefits of the above mentioned examples for the community. So at the end, I have to say that it has long been a challenge in many fields to measure atmospheric parameters in free space. And these can include any of the atmospheric quantities, including solid particles like dust or other air pollutants. This can include radiation, light pollution, gases, really a very wide variety of quantities. Here we can see a summary of what the methods are currently used to measure or to perform atmospheric measurements. And here there are advantages and disadvantages. So I would like to stress which are the most important ones. So nowadays we very often use static or mobile measurement stations. They have a very limited area coverage, and of course they do not use the real-time data to respond somehow and change the measurements accordingly. Very are balloon measurements, which provide us with some kind of vertical atmospheric profiles. They have this disadvantage of being unable to perform in bad weather. And of course, there is also no real-time response to data. It is caused by the fact that they are not controlled. So you cannot somehow change the direction and measure the areas which seem interesting for you according to previously measured data. Then satellite imaging can provide us with some really helpful measurements, but its main disadvantage is that satellite time is really expensive. So they are not used so often. And then we have this group of manned and unmanned aircrafts. Manned aircrafts have an important advantage of being able to respond to what you measure because they are controlled, they are piloted. But they're extremely expensive and they're not used very often for this reason. Manually controlled UAVs, which nowadays mainly involve multicopters, are seeing their beginning in this field, and they're still not used very often. And their main disadvantages is that they really cannot do a good job when the weather it's bad. And again, you cannot change. And they mostly do not use the measure data to somehow respond in real time to what you are measuring. So from all of these, you can see that the main challenges we're facing in this field are whether to make a system that is flexible or whether to make it specialize on one task. How to perform measurements under unfavorable or even extreme weather conditions. You can imagine, for example, thunderstorms. Measurements in thunderstorms would be very useful, but not a lot of systems are able to perform them nowadays. Then should the system be designed to be operated by qualified personnel, or try to design it so even lay person can use it? And again, we see this problem of using real-time data to adjust the measuring process. Now, I'd like to ask Roman to somehow summarize from our experience what should be the ideal structure of a system for measuring atmospheric parameters. So Roman, the floor is yours.
Thank you. At the beginning, and after answering all challenges question, we made summary of what such a device could and should be able to do. It results in a fairly complex description of the problem. The whole system of atmospheric measurement was divided into individual steps, which we can see in this picture. The primary thing is that we need to collect or measure some data with some sensor. For example, it can be airborne particles, radiation, or simple humidity and temperature sensor. The sensor of any quantity that interests us in 3D volume in space. Then we have to get the data from the sensor to the autopilot. This can be implemented by some device that reads the sensor and compose mumbling messages itself and send it to the autopilot. Or it can be programmed directly in the PX4 firmware. It is very useful to log this data on board because this log is not affected by subsequent systems as telemetering. It requires high quality and high reliable data links. The autopilot sends data to ground station, and there can be some visualization or some algorithms for planning trajectory.
Thank you, Roman, for this summary. And now let's see the examples of the measurement systems that is based on a project that we've developed. It's called ATMON, Atmospheric Monitoring, which try to somehow overcome all of the challenges we mentioned before, in that it's trying to be universal and fast for implementing new sensor. It's platform independent, so multiple different UAV platforms can be used can be selected and used with it, and it's trying to be simple and user-friendly. For example, in very simple geofence settings and visualization of the real-time measured data. Now, I'd like to ask Jakub to describe us how he used the system for measuring cosmic radiation in a scientific experiment.
Hello, here you can see a balloon scientific experiment. It is experiment for measuring of cosmic radiation in the ionosphere. It is platform for testing the future thunderstorm measurements equipment. The gondola was equipped by cell types of ionizing radiation detectors, two ion meters for positive and negative ions, 2 telemetry systems, and Pixhoff-based Autopilot. The total time of flight was about almost 2 hours. And the experimental payload mass was around 2 kilograms. The next slide, please. The experiment support avionics design is based on experiences from our previous balloon flight. Therefore, we choose the PX4 Autopilot, which is connected to GNSS navigation module, SIG modem, and LoRa-based telemetry system. The payload is connected by the UART link. It is bottom on the scheme, and this design features the gondola orientation, tracking, and logging. The use of PX4 stack simplifies the payload integration, and redundant telemetry links improve overall safety of the flight. Next slide. Yes, the flight. You can see a flight recorded by the Autopilot. The flight was completely covered by the telemetry data transferred, and the payload data was recorded in the onboard PX4 ULOG format. Therefore, it quite successful experiment. Thank you.
Thank you, Jakub. And now I'd like to ask Roman to briefly summarize and show examples of using ATMONs on drones.
Thank you. The use of ATMON on a balloon was one of the first use of the ATMON system. We also installed ATMON into UAV, and it provides us new possibilities in measurement of atmospheric quantities, because drone can be controlled. Our first measurement was a measurement of airborne particles, which have been selected because it's quite easy to simulate or create some artificial source, for example, by some fire. We tried to realize idle scheme that I described earlier, and here you can see a real implementation of ATMON in drone. At the beginning, you can see again a payload part. It is consists of a sensor and TF unipayload board. In our case, sensor was airborne particle sensor, and TF unipayload board is a universal interface between I2C sensor and serial Maverick connection to Autopilot. As you can see, there is a direct connection between global navigation satellite system and TF unipayload board. It is because sometimes it is important to have a very accurate timing, and our GPS receiver provides a PPS signal output that is connected to unipayload board. It provides possibility to align sampling of quantity from sensor aligned with some time mark. FIK-6 Flight controller provide us logging of measured data in form of microlog data files. Autopilot also retransmit Mavlink packets from payload to the ground station. Where is some server that is consists of database that collects measured data in real time and preprocessing scripts that prepare data for real-time visualization. Operator and pilot can use this real-time visualization for changing flight trajectory. This can be also done automatically by some script that recalculate or replan trajectory based on measured data, and this algorithm can provide new trajectory and send it through Mavlink to the Autopilot. Here is possible to see a real implementation of MON, some prototype board, sensor, and GNSS receiver. Now we would like to show you a video from the demonstration flight of Autogyro that was equipped with an airborne particle sensor. Fire pit was a source of pollution, smoke. Launching of our Autogyro. Operator can see measured data in his tablet. The Autogyro is flying through smoke from fire. The fire was selected because smoke from it is possible to see by A, and here is visualization where operator can see color spots that that shows where is and color shows concentration of particles in air.
Okay, thank you, Roman, for examples of using the system on drones. And now, at the end, we'd like to summarize the benefits for the community, for the drone community and the PX4 community. So maybe Jakub wants to start by mentioning some of the benefits.
Yes. The first benefit could be the support of the new platforms. For example, there was a balloon and autogyro, and the experiment or the system also improved the flexibility because we tested the PX4 stack in the new environments and very wide of area of interest on and in very harsh meteorological conditions. Yes, Herman, could you continue?
Our design forms the basic framework of the entire system, which can be expanded by users according to their requirements. The system is open to implementation of new sensor or sensor of new quantities, new algorithms, or new ways of data processing. The complexity of our idea is very important because high complexity means that user can use as it is, and developer can improve only part that he need or that need some his customer. This implementation covers a large part of the standard measurements, which are made in atmosphere standardly. In combination with algorithms for in-flight trajectory replanning, it can very improve the quality of measurement. It can reduce the cost or make measurement more efficient and reliable.
Okay, thank both of you for your contribution, and thank all of you who are watching us for your attention, and we hope that it can benefit also you as well. So now we are ready to answer your questions. Please don't hesitate to post question either in the special Q&A section or in the regular chat. So let's see. Okay, Farhank has a question that what is the reason behind using LoRa for communication? So it's probably for Jakub.
Yes. The main reason for using LoRa is for the backup of telemetry links, because in the balloon flight is quite a long flight trajectory, about 80 to several hundreds of kilometers. It could not be exactly predicted before the flight, and we have no evidence that we could cover the area of the flight by the standard SIG modem or direct connection to our ground station. The ground station in this particular experiment was realized by mobile cars equipped by antennas. Therefore, we equip the gondola by LoRa as backup, which connect the gondola system to the IoT network. The Things network was used in this situation, and this transmission covers the essential data from the gondola, like position or the speeds or altitude, and it was intended to be used to found or seek for the lost gondola in the case of the main telemetry link could be corrupted by some incident or not or not be available for some reasons. Therefore, the LoRa was a backup, but actually the flight was covered by the SIG telemetry link.
Okay, so thank you. I hope it was sufficient for you. If you have any questions, don't hesitate to write and post them. Many people ask us, or we have some questions which are very often asked during such sessions, and one of them is, why don't we use companion computer? Why do we use the ground control station? So maybe if Roman can clarify this, why we have to use, or why we are using the system in such configuration.
Yes, we don't use companion computers because some algorithms, especially algorithms for trajectory replanning, are quite needs quite a powerful computer, and the mass of payload grows with this access. Next reason is that our access provides some visualization for operator and pilot, and it can be in one ground station together.
Okay, thank you very much. We have some more minutes, so maybe we can clarify another thing, which is also often not really clear for some people, and this is why we are using, or why is it advantageous to design the balloon with PX4? Why don't we use a system that is like specifically designed just for balloons? Maybe this is a question for Jakub, as he was a part of the experiment.
Okay, the main reason was because in scientific experiments like a balloon flight, there is the main scientific experiment like ionization detector at our case, and the ionization detector needs some metadata for correct processing of the measured values or data, because for example, in the balloon flight, we should know the orientation of the balloon gondola, because some measurements are depends on the orientation. The ionizing radiation is the example of that, because in the case of different direction of the sensor has a different sensitivity. Therefore, we need some universal system to capture the metadata like orientation or position or altitude to calculate a correction for the other sensor, which is a scientific payload. And
Jakub, sorry, this session is scheduled to end in 1 minute. Okay.
Okay. The reason is we need the other data in standard format to be concatenate with the sensor data from the payload.
Okay, thank you. And then we maybe, Matthew asked whether we have a wiki or GitHub and any publicly available documentation which we have, and could Jakub or Roman provide it in a chat for Matthew? Some links for the wiki or maybe GitHub with our project.
I have provided a repository where is some documentation about balloon.
So this
finding about our measurement about ATMON.
Okay, so this will probably be the end of the session. So Matthew, I hope you'll find the information, useful information within the repositories. And thank all of you for your questions and for your support, and have luck. Goodbye.